Okay. Hello. Hello. Madison. Who else is connected? Hello, May.
Hi, Professor Curie.
Oh, okay. Thank you for confirming that you can hear and just share screen. Okay, so who we are and what are we doing? Or it's too early for me to ask this question because we didn't start anything. So this is a physical chemistry class, and I don't remember what I was telling you last time. Probably some motivation why physical chemistry is needed, right? And I'm not sure if you believe it, but I think we were making some connections between molecules, like chemicals, and properties of an electron, right? And then I was probably advertising the necessity of some math to describe electrons. So we need the way to describe wavy motion of electrons. So let's do an experiment with a rope. So their tail. Here. And hold. And you will be the observer. It's the longer the rope, the better. So you hold it and just lift it up and just try to shake. Can you make bigger tension and okay, and shake it more vividly, even more, like with higher. Okay.
Like at the same time.
Yeah. No, not hitting. Okay. Keep. Let me try.
Yeah.
So I don't know how to. Do you see? Let's make it still once again, so that it doesn't move. And now just shake it once. Just once and stop. Do you see something going from her to me? What it is? Okay. Yep. So basically, you can keep playing with it in the class, but basically we are done. This is what we needed. The electrons are like ropes,
Yeah.
or guitar strings, or the sound waves, and we need some math to describe it. Yeah. So what is a wave?
It's a signal.
Okay, so something is transmitting through space,
Yeah.
and it is changing over time, right? Yeah. And it has some fringes.
Mm-hmm.
So some fringes or some shapes that are transmitting through space and time. Good enough? Yeah. Okay, let's see if I. Yeah, those are recorded meetings from one of previous years. If you do not find me speaking clearly, you can enjoy it in recording. So we need traveling waves, and it is basically what we are going to come over. So the goal is to have wave equations, and then before we go to electrons, maybe look on the examples from more common sense. But probably we'll finish somewhere here today. We're not going to. We'll start slowly and we'll intensify by the end of the semester. So or just noise. How do you like this equation? Can you read it? And just tell me what is your impression? Like f is some function, right? And how do you interpret the fact that the arguments of the function are different in the left and right part? When I first saw it, you probably saw this equation before. I first saw it in high school. It was killing me because, like, how can you make two things to be equal to each other if they're not equal?
More like the function of x is changing with frequency and time.
Yes, but there is no frequency. It's more like velocity, right?
Oh, velocity. Okay.
So, Lola, have you seen how we were playing with a rope?
Yes, I did.
So, please remind me your name. Sibel. When Sibel sent a signal to me, it curved the rope, and this curved shape was moving in space. So the rope itself was not moving, but a little distortion from the center was moving.
Mm-hmm.
The shape of this distortion was approximately the same after some time, a different position.
Mm-hmm.
That dependence on position will be the same after some time offset.
Right.
But it will be centered at a different point. Like if you have like a little bump that moves, already some more complicated. So this is a definition of a wave which is quite general. So anything can fit in it.
Sorry, so x in this context is position, right?
X position t is time v is velocity.
Okay, thank you.
Signal was going with some velocity, and if we yell at each other, this yelling distributes with certain speed, like 300 meters per second in air. If we shine a laser pointer to the space station, probably the signal they will not see it, but it will propagate the speed of light. And if we speak about electrons, they also have their speed, which will be not constant. There will be different laws, but we can at least think about velocity, speed, just for our for the beginning of the considerations. Okay. I think I showed the answer, and now I'm asking the question. It's all upside down. Probably I was intending to ask you, like, which question can you ask for this answer? Now, if Sibel would send me a series of signals, like shaking, it will go like a sine or cosine wave, right? And then, depending on how frequently we transmit the signal, there will be offset between humps, right? And what's the name for this distance between humps?
The wavelength.
Correct. Yeah, if it is a wave and there is a length, then it is a wavelength. And then if we make a photograph, if like we recorded the meeting and then make a snapshot, and we see this oscillating rope, can we feed it into the like trigonometric function of cosine? Right? So where would the wavelength come into the argument, into the numerator or denominator? Well, it's like a silly question because it's already shown on the board, but don't you agree that wavelengths come into the denominator, right? Why? Because cosine is periodic as function of angle, which is in the units of radians. And if we want the integer number of periods, we want everything, a factor after this 2 pi to be 1. And 1 will be achieved when x will be equal to the wavelength, to lambda, right? Or when it will be like integer, when it will be twice as big as 1. Then we'll have this cosine. Okay, so now suppose I will look on the world by the eyes of a worm that doesn't have three-dimensional vision. I will look only on narrow slice of a space where this rope comes up and down. So I will not see how it is distributed in space, but I will see that it goes up and down, up and down. And I can look how this also oscillates so many times per second, right? So period goes to denominator, same as wavelengths, right? Okay. And now if this stuff is moving forward, we can just put position minus something that looks like velocity times time. Right? So this is more specific, more narrow definition. Before we defined wave of any shape, now it is trigonometric sinusoidal wave, but it matches. It is an example. So if this wave is traveling, how can you name it? It's not a question to scientists, it's more a question to philosophers and linguists. If the wave is traveling, this is a traveling wave, yeah. So names are made by humans for humans. Okay, so here is an example of equation for traveling wave. Function of position and time, and includes wavelengths and period. Now, you already constructed it. Let's unwind it and make one more experiment.
I must tell you something. I was trying to wrap it up. It does snap fairly easily. In 2 places, and this white powder came in. I can get you a new room.
No. That's fine. That's fine. But please keep. We need to rotate who is doing the experiment, right? Otherwise, someone can feel jealous. Like, oh, I didn't touch the rope this class. We like to come to the different corner to the class, and we'll do one more experiment. Lola, do you see this in the camera?
Yes, I do.
Okay, keep it. Not very strong rope. Okay, it will create some memories. It was sitting on my roof for the whole summer, and maybe degraded because of the UV. So we should be gentle. This one. So now do not make it tight so much, but let's try to send signal simultaneously. Like first, a little trial. Send signal. Repeat your name.
Joe.
Joe. Adam. So Joe sends signal to Adam. Okay. Wait until it calms down. Now Adam sends signal to Joe. Okay. It's not perfect, but you see something is going as we described. Now on the count 3, try to send signals simultaneously to each other. 1, 2, 3. Maybe lift it a little higher and try once again. 1, 2, 3. Maybe not less tension and make it small amplitude but sharper. 1, 2, 3. Ah, yeah, you saw it? So 2 signals are coming to each other. You can sit and stop playing or keep playing or pass it around, but it was the main message. So what happens if 2 traveling waves are coming towards each other? So let's discuss and describe it.
So the collide.
Well, if like 2 material objects, they collide and go to different sides, but waves can penetrate through each other, right? The signal will still arrive to the destination. Or if you make, if you throw a stone into water, right? One stone, another, and they make fringes, but they propagate independently. Or if we try to play Star Wars, take laser pointers and try to shine in different sides. It's not laser sabers, it's just the laser pointers. If the rays are crossing, they do not disable each other. You cannot like apply pressure and protect with one laser pointer against another one, right? So they do not, in some sense, they interfere, but they do not cancel each other.
Yeah.
There is an interference only in the place where they apply. Yeah, I have an idea that you can teach this course for sure. Maybe after some introductory, when there will be hard material, then for the easy stuff I will do, or it will be harder and will be asked you to do a couple of lectures. Okay, let's have two traveling waves. What happens if we change the sign here from minus to plus? What would it mean? It means we change from Joe to Adam, right? So it changes the direction of velocity. So now let's think if we have two waves. My calligraphic typing stopped, and here is ugly writing, but it's quite simple equation that you can see. So there are two cosines, one has plus, another has minus, right? And you saw that they collide, and in the range, in this area of the string where they appear simultaneously, it is neither first and neither second traveling wave. They somehow interact. We could do a third experiment if both of them like shake it simultaneously like crazy. What would happen? And basically, at the very beginning, you did it, right? And then it repeats the same shape, going up and down, but the shape is the same. Same as when people are jumping over the rope. So now we are going to go over the same idea with boring math. So we have one traveling wave. So here is x minus t, here is x plus t, and all this stuff like 2 pi wavelengths and period. What do you do when you see summation of two cosines? I say I hate it and leave the room, right? But if it is an assignment in high school for a grade, did you have the product and some equations in the high school? Or right? Or maybe it's some like elementary math in college. So the sum of cosines can be converted into product of like sines, cosines, and opposite way. Do you remember this? Does anyone remember this equation? I don't remember that myself. But you know that we can go into Wikipedia and recognize them, right? So this is a stuff that I really hated since high school, but now we need to go over. So it is 2 pi x divide lambda. 1, 2, 3, 4, 5 symbols. Too much for lazy person like me. I will just put alpha. So, and cosine is 3 letters. I'll put just C. So cosine alpha plus beta plus cosine alpha minus beta. Or under alpha and beta, we understand all this like wavelengths and position. So if we look into Wikipedia, and did anyone look on the link that I sent? So please catch me if I'm wrong. So cosine of summation will be product of cosines of two arguments plus product of sines of arguments. Right? Cosine of subtraction will be product of cosines minus product of sines, right? And if we add together these two things, so cosine of summation and cosine of subtraction, then product of sines will cancel out, correct? And we will have 2 cosine of the first argument times cosine of the second argument, right? Basically, we are done, but I'm going to unwrap it back. I hope that years ago I did slides for it and unwrap back. So now under alpha, we need back x divided by lambda times 2 pi, and under beta we need t divided by period times 2 pi. I think I was planning to draw on screen. Whew. Okay, so it is here. I apologize for very ugly calligraphy, but I hope you can recognize it. Let me know. If you hate it, I'll try to write it uglier. So two traveling waves, when they are collide, if they were periodic or sinusoidal waves, they create these patterns. So one pattern is periodic in space, and you had this like half period of cosine that was going up and down, right? You saw it. And another is just time dependent because it went up and down, right? So by sending towards each other two traveling waves, you can obtain one standing wave. I didn't play with the words, but if the wave is not moving, it is standing, right? Any questions or objections on this ugly equation? Or beautiful equation in ugly writing? All good? Now, I'm coming to the main part of our today's meeting. Yeah, I hope that at the beginning of the semester, I will be matching time perfect. But as we maybe even you'll start earlier, and I will count minutes and then ask you to return this minutes by the end of the semester, sitting a little longer. I hope not. So, main goal of today's meeting. We do need an equation, a differential equation, that will generate this as a solution. Okay? Does anyone knows the answer? Rough idea? Or maybe you have an answer, but you don't want to disclose it to anyone. Does the question look legitimate and reasonable? More or less. So find such equation which will generate this function of two arguments as an answer. What is a little unusual? If we would take basic differential equations like introductory level, there will be always functions of one variable, and here there is a function of two variables, so it's already advanced. Like when there is one variable, it's ordinary differential equations. When there are two, the more it's partial differential equations. So it's already, it will be a very simple equation, but it's already something crazy. Now, we are not going to derive it rigorously, but we are going to show how to get this equation in a very convincing way. I hope it will be convincing. So the equation will be, right? It's not a big secret. I can disclose the answer. It will be second derivative of a known function on the left over second derivative of space on the left, then equal second derivative on the right of the unknown function. And this will be matching this stuff. Now, how are we going to arrive to this? We are going to do a little mathematical experiment. We are going to take derivatives of this function over space and time. Maybe you are a little surprised why I withdraw myself from the focus of the camera. The screen, the touch screen that I have shows nothing, and bothers me a little. I really wanted to be able to write something. Oh, okay, better. Perfect. So the function is sine 2 pi x lambda cosine pi t period. What's your name?
Josh.
Josh, will you please assist me?
All right.
Please come through. You do calculus?
Yes.
Okay. So let's do a little experiment and try to take derivative over x of this stuff. Like there is a product of two functions, right?
Yep.
Would derivative affect the cosine of time? Probably not. You can just rewrite this portion as is,
All right.
and then apply derivative only to this one. And now we take derivative of cosine. Yeah, minus one. Okay. Then the argument is repeated as it was, just the same thing. So, and then if it is a close the bracket, and then it should be derivative of the whole argument over the x, right? Which will be the
Yeah, so then it just would be the 2 pi over the
x. Yeah, excellent, correct.
Yeah.
Yeah. Keep writing it.
Yeah.
It's okay. It's okay. We understand what you're doing. Now at least you can be. Yeah. Thank you. Thank you so much.
That's a bit.
Yeah, thank you. So at least now you can be empathic to me when I draw something ugly, because this stuff is not perfect. Okay. So it was the first derivative. Now it's a way to learn the names. What's your name?
Why?
Wyatt. Let's try to do second derivative, which will be applying the derivative to over x to this function once again. Let's do different color. Remove keyboard because it plays tricks on us. Escape. Yeah. So repeating the first thing unchanged, then taking a derivative of sine, which will be a cosine. We all understand it is x. And is there anything else? The derivative of the this factor appears. Yeah, please do. Yeah, thank you, Wayne. So, what are our observations? When we went from the original function to the first derivative, we got sine in one of the functions, right? But when we did derivative for the second time, we reproduced the original function once completely. It was so the second derivative of function equals to this minus 2 pi over lambda squared times function itself, right? So second derivative equals to the function. Okay. Let's see if this is what you already did it as an experiment when you were shaping the stuff. So okay. Is it okay if I will not call everyone today? You have a chance to write something maybe next time. So this is what Wyatt and
Josh.
Josh. So Josh and Wyatt did this experiment, and here I practiced laziness. So instead of pulling this long cosine over time, I just named it by a letter T, right? And then first derivative gives minus sine, second derivative gives cosine, and there's 2 pi over lambda squared, right? Now, if I practice the same exercise with second derivative over time, and for laziness, I will call the thing that the cosine of x just as x capital. Otherwise, I will be too exhausted. So first derivative changes sign. And may change cosine to the sinusoidal function. Second derivative changes sinusoidal to cosinusoidal. And we again reproduce the function itself. And now we can see that second derivative over position, if we divide it by minus 2 pi lambda squared, and second derivative over time, if we divide it by minus 2 pi over t squared, then they will be equal, right? So it can be considered as a surprise or as a wonder if you never did it. So applying second derivative over one variable, applying second derivative over another variable brings us the same result, which means second derivatives of this function over position in space will give us this function. Or if you know how to solve differential equations, by solving this equation, we will get our waves, both standing and traveling. When we make fraction of this lambda squared and t squared, 2 pi cancels, and lambda squared over t squared will come as a velocity, because so much of the length is accomplished by traveling over so short time. So it is velocity of the wave. So before we had standing waves and traveling waves, and this is any wave. And this is equation to get the wave. So how would we call this equation?
The wave.
Correct, yes, wave equation. So fortunately or unfortunately, exactly this wave equation will not be applied to electron. It will be a little modification, but general principle that will be very similar. So it will be equation where on one side we have derivative over time, on another we will have derivative over space. And then it will give the solution, which is wave both in space and time, right? So it gives us just general perspective where we are looking at. Okay, 29 minutes. What else can we do? Okay. Any questions about the wave equation? Can you reproduce it in the middle of the night with closed eyes? Yeah, I'm not going to make a quiz. I just curious. Like, do we need kindergarten level memorization equations, or adults and basic principle? Second derivative of space equals to second derivative over time. Over time, second what? Derivative. I'm not going to do it. So it's wave equation. Now we need this wave equation works for guitar strings, for the ropes, for the electromagnetic radiation, for the surface of a drum, which is also like has waves for sound waves in the trombones and trumpets. What else? Well, there are several examples, but electrons are very different things, and we need slowly move towards electrons because they are key factor for chemistry, for physical chemistry, and for stability of molecules. We need this SPD orbitals, which will be solution of the equation like this one, but with some specifics. So if you want to start slowly, I want physical chemistry and more narrowly quantum theory of electrons is one of the most counterintuitive areas of science. It's not as complicated because humankind works with it for almost a century, but still it is not as intuitive as several other branches. And I'm going to mumble a few more things which will set up a little bridge between common sense and wavy nature of electrons. Now all our screens or TVs are flat, right? With light emitting diodes, OLED, quantum dot LEDs, right? But the ancient computer monitors and TV were not flat, right? So what is inside of the non-flat ancient monitor? How was it engineered?
It's like kind of like electrons like shot through a small hole in a vacuum tube.
Exactly. Right.
And go to like some fluorescent surface that would flash into an electron hit it.
Absolutely perfect. Yes. Everyone agrees, or it needs more explanation? Yeah. Thank you, Josh. How would you deflect electron from a straight line?
Like by using light charges or power.
Yes, because electron is charged particle. If you just put a little capacitor, apply voltage, then it will deflect the string, right? So there is a like electron gun, which is also like high voltage that accelerates electrons. And in the actual TV, one make this electron ray to scan the screen, then modulate intensity, and then it makes the images. But what if we just have this non-focused electron gun, and then make a little screen inside this vacuum tube and punch two holes, with understanding that on the screen there is a scintillations, there is a fluorescence when electron hits the surface. So what do we expect from the common sense expectations? Like if there is a source of this ray, if there is a little punch, where will you expect the signal to appear? Straight line, like geometrical optics. And when people were designing this stuff, they were expecting it to behave this, to do this way. But if you place this slits, this punched holes close enough, there is something that goes against the expectations. There will be flashes in between. which is one of the proofs that electron is not a particle but a wave, right? So if you think of electrons as a waves coming, like if it is a surface of a lake, we throw a stone here, there are little channels. These channels will be like sources of the waves, and there will be fringes everywhere, right? On the straight line, maybe there will be maximum, but there will be something in between. So electrons are waves of something. And I cannot bring this equipment as a rope to the class, but I just invite you to do it. So electrons have wave nature, and we will apply equations similar to wave equation to describe them. About in the middle of semester, we'll make a vote if you prefer exam or project, but through last 10 years, everyone was selecting projects. And I'm going to show one of the outcomes of the project that is kind of the simplest one, but it is good project for those who select future career in the education, because the little thing that I'm going to show comes out of the simulations that one can do with MATLAB by the end of the semester, but it will be an illustration of the simple hypothesis of the electrons moving like on a circular orbits, but carrying wave in nature. So it's like waves obeying electronic progress going on circles. And right now, I'm going to show it not as a big scientific demonstration, but more like entertaining factor that shows something that will keep us interested and motivated.
Never gonna let you down, never gonna run around and desert you, never gonna make you cry, never gonna say
you see, there are waves that are going on circles, and they have different wavelengths, right? And they move both in space and time. And there is thing that changes up and down, and there is a squared that is almost stable. So the images on the left were showing these oscillations, and they look more or less beautiful. And those on the right were looking ugly, right? So here there is an integer number of waves along the circle, and here is a fractional number of waves along the circle. And basically, I can squeeze in the remaining minute the whole course, but there is a beauty criterion of math. The solutions that look beautiful are correct. The potential solutions that look ugly are wrong. So basically, those which are beautiful will satisfy equation, and those ugly will not satisfy. So those will be correct equations that one can obtain by pen and paper, and those only ugly simulations that will not exist in real nature. They will decompose in something. Whew. Questions? I think it's enough new material. Questions 1? Questions 2?
I have a question.
Yes, Lola.
Sorry if I missed it. What does M represent in this context?
It's number of nodes. It's like 2 maxima, 2 minima, 3 maxima, 3 minima. So it's like a Bohr model with how many full oscillations wave gives across this period, across the circle. So about in lecture number 40, we will revise Bohr model after you pump our mathematical muscles, we will return to very basic concept and solve it, and we will get the same answers just by pen and paper. Should I speak about this model a little? So it's I will try to bring maybe more models anytime I come, if I don't forget. So it's one of the research which is already completed, but silicon, which looks like carbon tetrahedral diamond, and a couple of atoms are replaced. Instead of silicon, it's like phosphorus and aluminum. The neighbors in periodic table, phosphorus has one more, aluminum one less. And when they are in the same structure, electron from phosphorus goes to aluminum, and it creates dipole and charge imbalance. If you fully excite, it goes back. But if you connect stuff around with a metal wire, then instead of going through the thing, this current upon excitation, de-excitation will go through metal wire. So excitation comes through wire, current goes through wire. Basic principle of photovoltaics for solar cells. So n-doped and p-doped silicon interface. Done, enough. I think my 50 minutes have expired. I'll stay here. You're welcome to approach and ask questions if you need, but probably you are on schedule. You need to. So have a nice weekend. No homework this time. Looking forward to see you on Monday. Stop sharing. Everyone is connected.